Okay, hi everyone. Very good afternoon to you all. I am Amir Hamzah Abd Ghafar from University Putra Malaysia. So currently I'm talking here to you all from Malaysia. We are, I think, 6 hours earlier than you all. Most of you in Europe. So here is already late afternoon. Okay. In my talk, the title of my talk is partial key exposure on RSA using Dickman's function. So this is the contents of my talk that I will try to finish in about 20 minutes or 15 minutes. Okay, so parts of this research actually has been published in the Mathematics Journal last year. And the part of this work actually is my part of my PhD thesis. Okay, I recently graduated in 2020, and now working at University Putra Malaysia. So let's have some introduction of the partial key exposure attack. Most of members of cryptographic research here maybe already know what is the partial key exposure attack. So partial key exposure attack is actually cryptanalysis with an assumption or precondition that the adversary has known partial private information regarding the cryptographic system that he or she wants to attack. Well, so how this information can be obtained or can be exposed. So the information of the private keys can be exposed via attack called side-channel attack, and this side-channel attack introduced by Koch et al. I think in 1996 using a very popular timing attack. It also covers computational power, emission of electromagnetic power, acoustic pattern. They are all can be released by the cryptographic devices. So it's a very huge field of such an attack. Okay. So the immediate effect of this attack is that first, it does not have any impact on the security of the crypto system. However, the exposed info can lead to a more complicated and damaging attack, meaning that the data exposed from such an attack can be helpful for the adversary to conduct another attack, and that's what we will do here. Okay. So what my research focus on will be focused on the CRT-RSA. So as you know, the CRT-RSA or Chinese remainder theorem RSA is one of the variant of a standard RSA crypto system, and is proposed by the creators of RSA in their patent application. The rationale of using this CRT-RSA is to utilize much smaller parameter size in the algorithm that which we will see later. Okay, so this is the CRT-RSA key generation algorithm, and as you can see, the difference in the CRT-RSA key generation algorithm is that they will have two decryption keys, DP and DQ, such that these two conditions satisfied. And of course, we can still use the normal or the common value of public key, which is E equals to 65537, because the condition for E is just that E should be less than Vn, and the GCD E and Vn is equals to 1. And in the encryption algorithm is just a normal one, meaning that it is similar to the standard RSA, while in the decryption algorithm, this is where it differs much. We have to compute these three computations, which actually is more efficient rather than one computation of modular exponentiation in standard RSA. So that is why CRT-RSA is very commonly used in our industry today. So in our research, we want to attack the partial key exposure attack against a CRT-RSA by identifying parameters, condition, the size of parameters, and how much information can be exposed. enable our attack. Okay, so that is our objective. So let's have some literature review very fast here. So there are some partial key exposure attack on CRT-RSA, and the common goal or the common aim of this attack is that we can factor n, which is the RSA modulus, in polynomial time. So we can see here there are 4 methods using the lattice-based method, and also we can also use the random reconstruction algorithm to factor the n in CRT-RSA in polynomial time. So let's go on to our attack. So in our attack, we must have this lemma to help us. So actually this lemma want to obtain an approximation of P called P tilde, where the modulus of P minus P tilde is less than n to the power of 1 minus alpha over 2, where alpha is actually the fraction of the most significant bits of P or Q unknown. So this is where the partial key exposure occurs, okay? When we have the assumption that the fraction alpha of MSB of P and or Q unknown, okay? So another parameter that can have the exposed info is dp, okay? It's dp, which we can see in this lemma. By knowing the fraction of alpha of most significant bit of dp, we can also it can eventually lead to the exposure of the constant kp in the RSA key equation. So by knowing the partial bits of dp and p, we can conduct our attack. Because in this proposition shows that by knowing these two values, okay, we can see that it can derive dp, okay, it can derive dp. But noted here, observe here that we still need a value of the floor of p minus 1 over e. Okay, we still need this value here. And by combining all of the results in the lemmas and in the proposition, we can have this theorem that ultimately state that if we have A1, where A1 is actually this value, sorry, not this value, this value, okay? A1 is one of the prime factor of this value, and have the alpha fraction of most significant bit of dp or p or q, then we can factor n in polynomial time. So that is the ultimate result in our attack. So from here we can see that it's very important to know the factor of p minus 1 over e, so the floor of it, to conduct our attack. And this demonstrates that we can reduce, okay, this is very important observation that we make. We can reduce the hard problem of RSA from factoring n to factoring the floor of p minus 1 over e. So we can redirect our focus here, our energy here, our mind here to factor the floor of p minus 1 over e. However, of course, the complexity of this factorization is still sub-exponential according to the current factorization technique. So these are all the parameters that should be known before the attack, should be known during the attack, and should be known after the attack. Okay, and we can also conduct our attack in this manner or in this algorithm. So what is the big step to achieve this condition? That is the value of A1. So the value of A1 is the most crucial parameter, and it is the largest prime factor of this floor of p minus 1 over e. So so now our next step is that we have to find the value of A1. So by how? First we try to keep the candidates of A1 first. Okay, we try to determine the candidates of A1, So by having this proposition, we actually can see that this is the estimate number of candidates that are eligible to be A1. So this proposition is actually based on the prime number theorem. And we can see here, if our exposed info alpha equals to 1/4, the number of candidates will be here. Okay, n to the power of 0.37, which is actually is a very large number. So meaning that there are a very large number of candidates of A1. So it's infeasible for us to conduct search of A1. However, by defining our success appetite here, okay, so we define this success appetite as that as the conditional probability of successfully finding the largest prime factor of A1. The largest prime factor of P minus 1 over E, which is A1, where A1 is less than n to the power of y1. So this is the success appetite. So by having this success appetite, we must use a function called Dickman function. So this Dickman function is actually not a recent function, quite old function introduced in 1930. So this Dickman function can be used to solve this question. That n be a composite number, what is the probability that the greatest prime factor of n is less than n alpha for alpha less than 1? So specifically, this function is used to determine the distribution of the largest prime factor of a given value. So we use the Dickman function as a tool to redefine our success appetite. So this is actually the Dickman function, and this is the example of a Dickman function. For example, if we have zeta equals to 1/2, this means that for any random integer n, meaning that it's not the RSA modulus, is a random integer, composite integer, there is a probability of 0.3068 that its greatest prime factor is less than n to the power of 1/2. So that is one example of Dickman function. So we use this Dickman function to define our success appetite, and we can see that if we putting in the values of the success appetite or the success probability with the value of alpha, which is the exposed info, the MSB, okay, leak, we can see that if we have a smaller success appetite, we can have our n to the power of 0.4208 when success appetite is 0.01 and alpha is 0.05. And this number will be smaller and smaller if we have a smaller success appetite. So it's logically will be like that, all right? So we compare our attack with this result from previous attacks. And so that is the comparative analysis of my work. So as a conclusion, we have seen that we can factor the modulus of CRT-RSA in polynomial time using this new method under specific condition. And what more important is the point number 2, which is our attack requires the largest prime factor of this one. So that's why I need to re-emphasize that maybe we can redirect our approach by factoring n, where we know that n is equal to PQ and P and Q are two large prime. So we can redirect our energy to try to approximate the value of this floor. And because this floor should be easier to factor, because this is not substituted of two large prime factors. It can be, I don't know, constituted of several primes, right? So this work want to make us rethink about the approach. Okay, so that's why I said in future work we should have some approximation of this value, and to find a new method to find A1 from a smaller set of prime, and maybe we can use the machine learning technologies with the aid of the clock system to reduce the number of prime as candidate of A1. So these are all the references. And if you have any question or any inquiry, please contact me at this email. I'm sorry if my talk is very fast, but I need to deliver my idea within this time constraint. Okay, so thank you very much for listening.